Okay, for our first question, it is a saturated water, and these are the given. So I first determined whether the pressure and temperature given is superheated, compressed, or LV mixture. And in our case, it is superheated. And with the superheated table, I determined the specific volume is 0.52261 meter cube per kilogram. And the needed value or required value in the question is the area. So I use this formula. Mass flow rate is equals to area times velocity over specific volume. I use this formula and determine the area using these values, these three values, which are the mass flow rate, velocity, and specific volume. And the answer is 0.019232048 meter squared, or 0.0192 meter squared. So for our second question, we have steam or saturated water again, and these are the given for inlet and outlet. So first I determined whether the inlet pressure and temperature superheated, compressed, and or LV mixture rather. And it is for inlet it is superheated, and for outlet as well it is superheated. For the inlet, I using the superheated table, I determined that I determined the specific volume and the enthalpy. And for outlet as well, using the superheated table, I determined the specific volume for outlet and enthalpy for outlet. Next, I list down my assumptions. First, it is a steady flow process. Second, it has no Q in or heat in. Third, there is no work. And fourth, PE is negligible. So I canceled out the values based on my assumptions, which is the work in, Q in, and work out. And I also canceled the potential energy, which is the GZ sub 1 and GZ sub 2, and use this equation. So since the Q out given is in kilowatts, which the value the unit for needed for velocity outlet velocity of the outlet is ms squared, or ms squared per second squared. I rather m squared over second squared. I used the mass flow rate to cancel the kj over s, because kilowatt is equals to kj over s. So I use the mass flow rate to cancel the seconds, which is this one. Mass flow rate is equals to a sub 1 times velocity sub 1 over specific volume, and I put it here, and which is equals to Q out times velocity sub 1 and area, rather specific volume sub 1 and area times velocity sub 1, which then I use the equations given for this. For enthalpy, I use this one and this one, and I Also, to cancel out the kilojoules per kilogram, I used 1,000 meters squared over s squared. It is the reciprocal of when we get the kj over kg of ms squared. M squared over s squared. And for velocity, I also input the values, and for the q out here, I use this equation, or read this equation rather. Next is when I put the values in the calculator, the answer is 604.71536 meters squared per second. So I canceled the unit that stayed was the meter per second over s squared, which is from this one and this one. So I added, so since it has the same units, I was able to solve the equations. For the volume flow rate, I use the equation of mass flow rate again, which is this one, and change the A sub 2 and V sub 2 into volume flow rate, which then we leaves us with this equation. Next, I input the values for specific volume 2, area sub 1, velocity sub 1, and the specific volume 1. As you can see, I canceled the cm squared in the given of area. I used 0.0001 m squared over cm squared to cancel the centimeters and change it into m squared. Next, to compute for the units, I canceled out the kilogram, which then we are left with m6 over squared times 1 over m3, which is from the reciprocal of that equation, which then the answer is m cubed over s, which is this one, and the answer is 2.56882173 meter cube per second, or 2.57 meter cube per second. Okay, next, for our last question number 3, we have a turbine and steam or saturated water again, and these are the given for inlet and outlet, and mass flow rate. So we have a mass flow rate of 12 kilogram per second. So I first determined whether the pressure and temperature is superheated, compressed, or LV mixture. For our inlet, it is superheated, and for our outlet, it is LV mixture, since we already have a quality. Next, I determined through the superheated table the specific volume and the enthalpy. For outlet, I use the equation specific volume is equals to Vf plus X times Vg minus Vf. And this is the answer. And for enthalpy, it is H is equals to Hf plus X times Hg plus Hf. And this is the enthalpy for the outlet. Next, I wrote down or list down the assumptions. First is the steady flow process. Next, we don't have a heat transfer, and third, we don't have any work in, and lastly, PE is negligible. I then canceled out the values based on our assumption first I canceled out the work in, Q in, and next I canceled out the Q out since it is a diabatic processor. There's no heat transfer. Next, I canceled out the potential energy, and which then leaves us with this equation, and I just wrote it in this form. Now, the values needed is the kinetic energy, work flow rate, and the area. But instead of computing for the kinetic energy, I um, computed the workflow rate already. So this is the equation, and I input the values for the specific value for the equation, and which then leaves us with workout of 851.8172 kilojoules per kilogram. I then multiplied it with our mass flow rate in order to get the get the power, or the kilowatt, the work in kilowatts, which then leaves us with 10,221.8064 kilojoules, which is also in kilowatt. Next, I computed for the kinetic energy, which is this one also, and the answer is 3.2 kilojoules per kilogram. And for the kinetic energy of the outlet, it is 1.25 kilojoules per kilogram. And for our last value, we need the area for the inlet of the turbine, and I use the formula of mass flow rate again, since we have the given of mass flow rate, which is the 12 kilogram per second, and I move the equation into this one, which then leads us with this answer: 0.0044673 meters squared for the area of the inlet. Thank you.